One day of calculus without a live teacher. Woo! Okay, so we're on day 3 today, according to the assignment sheet. So keep following the assignment sheet, you guys. The homework for day 1 and 2 was that worksheet. We're going to be book problems here today, and we're going to have plenty of time to be able to debrief these as we need to. So what we're going to talk about is a spinoff of the slices. So remember when we did slices, slices take 4 easy steps, right? And those 4 steps are all very necessary when you do a slice problem. But today we're going to talk about volumes using discs and washers, because the question is, if all the slices are the same shape, we could streamline the process. So basically what we're doing here now is we're shortcutting those 4 steps. So let's take a look at the shape that I have here on this first slide. It's this green ring. And I suspect that you're going to be fairly surprised by what I do next. But what we're going to do is talk about a disc versus a washer. So if I were to take this piece and move it away, yeah, you didn't see that coming, did ya? I bet you thought that was actually a full ring. No, it's not. It's a white circle inside of a green circle in order to get the point across. If I want to find the area of a disc would be like the green circle or the white circle by themselves. If I'm talking about a washer, does everybody understand that a washer is just, oh gosh, I moved it all over the place. A washer is just what you get when you just have that green ring and there's actually really physically a hole in the middle. So let's discuss here for just a moment, please, how we're going to find the areas of all those shapes. So if I wanted to find the area of the white circle, what we would do is to take pi times the radius of the white circle. So let's go ahead and give ourselves the radius of the white circle. I'm just going to call that r. And so then we'd take pi r squared and we'd get the area of the white circle. And if I wanted to find the area of, say, the green circle, the whole thing, I would take pi times the radius of the green circle. So we know that that white circle was on top of that one. The radius of the green circle, based on how I've got this now, if I start here at the center and go all the way to the outer edge, I'd say that that one, I'm going to call that capital letter R. Okay, so then the area of the full green circle would be pi times big R squared. So I'm using uppercase letter R and then lowercase letter r for the little radius and the big radius. So if we needed to find the area of, say, the green washer, what would we do? And I'm sure that a lot of people got it. What you would do is take pi times the big R squared, the green circle, and subtract off the little white circle. And those two circles both have pi in them. So in theory, what you would do is to just take pi times big R squared minus little r squared, close parentheses. And that would give you the area of the washer. And if you didn't have a washer, if there wasn't a hole in the middle, you would just have pi times r squared of whatever your disc shape is. So if we want to find something with a volume, what a volume does is it says that in order to get the volume, you're going to integrate a whole bunch of areas and then times that by d whatever. So let's start summarizing this on the next slide. I know you've been waiting, right? And so we can summarize this into the following formats. First format is your basic standard washer method, or sorry, disc. So please indicate, you guys, in your notes that this one is for discs. You're going to take the volume and say that it's always going to equal pi. And we're going to shove pi in front of our integral symbol because it's a constant multiplier. So we just get to work our way through our integral and then multiply our final answer by pi. And then it's going to be the radius squared times d blank. And then if you don't have a disc and you do have, sorry, not a disc, but you have a washer, then the bottom one is your basic format here for a washer. What I'd like you to make sure that you insert into your notes is the different ways that you could have your slices being done. If you have a slice that goes like this, and this is why we practiced what we've been doing the last couple of days, if your slice goes like this, then that means that your thickness is delta x, which means that that would be a dx type of an integral. If your slice goes this direction, and I don't care if you've got a disc or a washer, and we'll talk about what's the difference between them and how we'll know. then that means that your thickness in this case would be delta y or dy when you actually do your integral itself. Okay, the thing that you guys all need to know, and this is going to be something that everybody should please make sure that you've got written down in your notes, is, and put it in like a star or something to highlight it, you will always place your cuts perpendicular, I'm using the symbol here for perpendicular, to your axis of revolution. Let me spell that correctly. So if you're revolving around the x-axis or the y-axis or whatever line you're revolving around, always cut the shape up perpendicular to your axis of revolution. When we did slices, we were told. We're not going to be told anymore. So let's just go ahead and start doing some sample problems here, so you guys can get your feet wet into how this rolls. Let's just copy down these. Go ahead and hit pause. So on this first integral here on section A, it says, let's take that shape and revolve it around the x-axis. So this is what you guys are going to do when facing a homework problem, is first off, come up with your sketch. That's always going to be item number 1. And then revolve it where you're told. So we're going to go around the x-axis. And would you always please do me a favor, do yourself a favor, and show the revolved shape using dashed lines. And there's a reason for this, and I'll explain here in a moment. And then if we're revolving around the x-axis, then that means we're going to place our cuts perpendicular to the axis of revolution. So my cut is going to be perpendicular to the x-axis. And if my cut is one of these kinds of cuts that's perpendicular to the x-axis, then the thickness of my cut is going to be a delta x. This is going to be important for us. And we can look at this cut and we can say that it doesn't have any hole in it. And if there's no hole in it, then that means that we're looking at a disk. And the basic integral method for a disk is going to be pi integral blank radius squared times d blank. So I'm using blanks here because that's going to be your basic skeleton form. So let's fill in the blanks with what we need to do. And in this first blank, we're going to have, actually, I'm going to fill in the end here first. This is going to be the first one because I think we already know the answer to that is x, which sets off a chain of reaction. The chain of reaction is going to be that your limits of integration, then go back to the beginning, will be on the x-axis. Look on the x-axis at what I'm doing. All these cuts are going to be from left to right. So that means your limits of integration are going to be from 0 to a, whatever a happens to be. It'll be a number when we actually do problems. And then you need to find the radius, because inside here, you're going to need to know the radius of your circle, because this cut, remember, represents a circle. So here is your radius. And in order to get that radius distance off to the side, you would take the top of it minus the bottom of it. Now remember, the top is going to be some equation, and the bottom in this case would be 0, because the radius of the circle is going to be on the x-axis, the center of the circle. And so that would be an easy way for us to fill that one in. So what changes when you revolve it around the y-axis? So let's go to letter B. First, please go ahead and show your revolved shape using some dashes. Ugh. Sometimes the diagrams are really horrible, and I promise not to judge you if you don't judge me. Okie dokie. And then let's place our cut. And our cut has to be perpendicular to our axis of revolution, which means that my cut's going to have a thickness that goes like this, and it's a delta y problem. I don't see any big gap in my cut, so that means I'm going to say that my cut is a disk, and we will practice what happens when it's not a disk. These first two are disks, though, to begin with. And the basic disk method is to take pi integral radius squared d blank, and we're going to fill in the blank with the y. And that sets up the chain of reaction. So now go back to the beginning of your integral. The limits of integration are going to be on the y-axis, starting with the bottom cut all the way up to the top cut. So our limits of integration this time are going to be from 0 to b. And then the radius is going to be right here. And in order to get that radius distance, I'm just going to abbreviate it RAD. In order to be able to get that radius distance, you're going to take the right side minus the left side. And once you do that, based on whatever your equation is, you'll have your integral set up, and then you're ready to be able to solve your integral, do whatever it takes to get that volume. So now is when we practice. I've got 3 example problems, and we'll go through these and see how it rolls. We're going to find the volume for each of the following regions. So what we're doing is we're cutting out steps here, you guys. We're saying that you can just go straight from your sketch to your volume. So let's set up our sketch. I'm going to sketch y equals x cubed, which I know is this. Y equals 0, which I know is the horizontal line, y equals 0. It's really hard to see that right there. And x equals 2 is a vertical line right here. And what that does is it sections off that 2-dimensional area there in quadrant 1. I'm going to go ahead and color it in real quickly here just so that you guys can see this area. And I'm going to erase my highlighting because I don't want that to stay. Because I'm going to take that area and then I'm going to revolve it around the x-axis. So I'm going to show my revolved shape using dashes. And then I'm going to make my cut. And you have to make your cut perpendicular to your axis of revolution. So if we're going around the x-axis, I'm going to place my cut perpendicular to my axis of revolution. And that, you guys, begins this process. Because we can look at that cut and we can say that there is no holes in it. And if there are no holes in it, then that means that we're going to go straight to the next step and start setting up our volume. And our volume, we can say V is equal to the integral. It's going to be a disk. So I'm going to write down the word disk, because then I know that the disk method is pi integral radius squared d blank. Our job is to fill in the blanks. Specifically, here's my radius squared d blank. I'm going to start at the end by filling in x, because I know based on my sketch that if my sketch looks like that, that's a delta x thickness, which means then that my limits of integration are on the x-axis, starting from the left and going to the right. So that would be 0 to 2. And then the radius, and this is what you got to really watch carefully for here. Here is the radius. And you don't want to use this radius. They're both the same in terms of the circle, but that radius on the bottom would reference this equation right here. And that's our revolved equation, and I don't know it. I can figure it out because we're all smart enough, but none of us wants to waste the time doing something like that. So we're always going to use the radius on the non-revolved shape. And in order to get that, we're going to take top minus bottom. And the top equation was x cubed. And the bottom equation is 0 because that represents our x-axis, and our x-axis has a value of 0. So then you just need to finish the problem. So this is pi integral 0 to 2. X cubed minus 0 is x cubed, and x cubed squared is x to the 6th. And then you'd have a dx at the end. And then the rest is history, because you keep that pi, take your antiderivative, vertical bar 0 to 2, and then you can plug in your numbers. So you'll have pi times 1/7 times 2 raised to the 7th minus 0 raised to the 7th. And once you do the math, 2 raised to the 7th power is 128. So you'll have 128 pi divided by 7 for your final answer for this problem. And that's how it goes, you guys. So now let's check this out. Look at what I did to you. I gave you the exact same problem, the exact same equations, only we're revolving it around a different axes. So let's see what happens when we start adding in some other twists and turns. This time we're going to take that same shape and revolve it around the y-axis. So here's my same 2-dimensional shape that we had before. That was a 2. And if I revolve that around the y-axis, then my revolved shape is going to look kind of like that. Yep, you be nice to me and I'll be nice to you with all of these sketches. Haha. And we have to place in our cut perpendicular to our axis of revolution. So if we're revolving around the y-axis, perpendicular to the y-axis would be horizontal. And here is when we see we have a bit of a problem. Because in order to be able to make this cut happen, there's this big gap in the middle. Does everybody see this big gap right here in the middle? And anytime that gap comes, I'm going to erase that arrow that I just did. Anytime that gap comes up like that, that tells you that you are specifically working with a washer. This is going to be a washer problem. So when we go ahead and we start setting up our volume, we know that our basic volume on this one for a washer is pi integral bracket big R squared minus little r squared, close bracket, d blank. That's going to be your basic format for every washer problem that you encounter. So I'm just going to say V equals pi integral bracket. Let's leave a big space for big R squared. Leave a big parenthesis space for little r squared, close bracket, d blank. So once you set up your skeleton form, you can circle back and go to your sketch and say, wait. On my sketch, I know I sketched it like this. I placed my cut that direction, which means I have a delta y problem. So then you can go over to your equation and fill in that with a y, which sets up the chain of events that your limits of integration are on the bottom of the y-axis all the way to the top value of the y-axis. But the problem is that we don't know that top value on the y-axis. But what we do know is that our x value is 2. And if our x value is 2, then our y value must equal 2 to the third power. So our y value is 8. So our limits of integration are 0 to 8. And then we have to do big R and little r. And this is when I get into different colors, lots and lots of colors on my diagrams. So here's big R and little r. Big R is always the distance, and I'd like you guys to physically put a dot on your axis of revolution, and then physically put a dot on the outer edge of your axis of, or of your washer shape, and connect those together. And that indicates big R. Big R, in this case, since it's sideways, is going to be the right side minus the left side. So the right side is just the number 2. And the left side is the axis of revolution, which is 0. So it's just 2 minus 0. No big deal. Little r gets trickier. Little r is the distance from the inner edge. Again, put a dot on your axis of revolution, and then put a dot on the inner edge of your washer and connect those together, and that indicates little r. And little r would also be right side minus left side. However, the right side is going to be your equation. Now we have the equation y equals x cubed. I absolutely 100% cannot put x cubed in the middle of a dy integral. Does everybody see this right here? I'm going to erase it ultimately. But an x in the middle of a dy integral is illegal and wrong and will always be a dock of a lot of points. I can't put an equation in terms of x's in something that's dy. Instead, what we do is we go back to our original equation and we solve for x by taking the cube root of both sides. In other words, y to the 1/3 power is the equation we're going to use in place of x. So we'll say that our right side is y to the 1/3 minus the left side of little r now is still our axis of revolution, which is 0. Once you have it set up, in theory, the rest of it is a piece of cake because now it's just a matter of cleaning things up. So 2 minus 0 squared is, of course, 4. Y to the 1/3 squared would be y to the 2/3 power, and then this is dy. And then all we're left with doing is taking antiderivatives. So the antiderivative of 4 is 4y, and the antiderivative of y to the 2/3 is y to the 5/3. We'll put the reciprocal of 3/5 in front, and then we'll have a vertical bar 0 to 8. I'm going to keep that pi out front, and then I'm going to get ready for a bracket and plug in my upper bound of 8. So do the arithmetic. 4 times 8 gives you a 32. And then you got to plug in 8. And off to the side here, I'm trying to figure out 3/5 times 8 raised to the 5/3 power. So I'm going to take the cube root of 8 first and get 2. So then this is 3/5 times 2 to the 5th power. So then this is 3/5 times 32, because 2 to the 5th is 32. So times 32 with 3, and you get 96/5. And that's the answer that I'm going to put in my parentheses, because otherwise you just get way too bogged down with arithmetic. And then if you plug in your lower bound of 0, you'll just get 0 minus 0, which is kind of handy. So then just throw it into a calculator and convert it into a fraction. 32 minus 96/5 gives you 64/5. So don't forget at the end that your final answer isn't 64/5. It's 64 pi over 5. And that's what our final answer is there, which gets us to our last equation. And our last example, my bad. And I did change the equations on this one. So let's go ahead and come up with a sketch that represents this. And now what we're doing is we're taking something a little bit simpler in theory, y equals 3x, and we know that that's just a line with a slope of 3 that goes through the origin. Y equals 0 is my horizontal x-axis, and then x equals 4 is a vertical line. So again, what we've got then is this actual triangle shape, and we're going to revolve that around the line x equals -1. So don't worry about having any sketches drawn to scale. That's not going to be necessary. But if I show my shape and I'm revolving around that vertical line, I got to leave this gap distance. And I'm going to start showing using dashed lines to show my revolved shape. And once I get that drawn in, I have to start placing my cuts. And my cuts are going to be perpendicular to my axis of revolution. And I can see very quickly here that based on the look of my cut, that we are going to have another washer problem. So over here, I'm just going to start setting up my volume to be a washer. And it helps you guys if you write down the word washer, because if you write that down, then that helps you get some grounding in the problem itself. So then it would be pi integral bracket. Let's leave a big space for big R squared minus little r squared, close bracket, d blank. And then all we got to do is go back and fill in the blanks. And we're going to start at the end of the problem, because right here you can physically see that we made a cut perpendicular to the y-axis. And that was a horizontal cut. And if you have a horizontal cut, then that means you have a dy problem, which means that your limits of integration are on the y-axis from the bottom to the top. And it looks like on the top, I don't know that number off the top of my head, but I can calculate it, because if I know the x value is 4, then I can say that y is equal to 3 times 4, so y is equal to 12. So our limits of integration would be 0 to 12. And then I have to figure out big R and little r, and this is, I think, always going to be the trickiest part for you guys. Please put a dot on your axis of revolution and put another dot on the outer edge of your washer. Original side, not the revolve side, because we don't know those equations and we don't want to waste our time finding them. And if you connect those together, please label that capital R. And in order to get that length, you're going to have to take the right side minus the left side. And the right side is 4, and the left side is -1. So it's 4 minus -1. And then you'll have to get little r. And little r will be the distance from your axis of revolution to the inner edge of your washer. Notice how I'm putting my nice purple dots there, and I'm going to link those together, and I'm going to label this little r, and little r is again going to be the right side minus the left side. The only problem is that the right side is the equation y equals 3x. And if you go to your integral and you put a 3x in the middle of a dy integral, you will be wrong. So I'm going to undo my 3x there, and I'm going to go back to my equation, and I'm going to say that I have to solve it for x. So I'm going to divide both sides by 3. Dividing by 3 is the same thing as timesing by 1/3. So 1/3 y is what I'm going to fill into my integral. Oops, see, it's such a bad habit, you guys. I wrote 1/3 x. Even though it's 1/3 y. That's my equation. And I'm going to subtract off my axis of revolution, the left side, and the left side equation was -1. And then we can solve. It's going to take a little bit of work for us to solve this one, and I think you guys will see why here in a second. 4 minus a negative 1 is 5, and 5 squared is 25. So that part is not a big deal. But then inside this parentheses, we have 1/3 y plus 1. And we're going to take 1/3 y plus 1 and square it, which means over here off to the side in the bottom left-hand corner, I'm going to take 1/3 y plus 1 times another 1/3 y plus 1, and I'm going to FOIL that. So when I do first, I get 1/9 y squared, so I'm going to subtract 1/9 y squared. When I do the outers, I get a plus 1/3 y, and when I do the inners, I get another plus 1/3 y for a plus 2/3 y. Don't forget, you got to distribute your minus. So you're going to write down minus 2/3 y. And then this plus 1 times that plus 1 is another plus 1. But again, I'm subtracting everything, so I'm going to subtract 1. And then list a dy. In other words, this problem becomes pi integral 0 to 12 of 24 minus 1/9 y squared minus 2/3 y. Close parent. Oops, sorry, I totally fumbled that. dy. Keep the pi. The antiderivative of 24 is 24y. I'm going to keep that 1/9, and the antiderivative of y squared is 1/3 y cubed. And I'm going to keep that 2/3, and then the antiderivative of y is 1/2 y squared. And then I'm going to vertical bar 0 to 12. Cool. Check out that 1/2 and that 2/3. Those will cancel. I'm going to keep my pi just as a multiplier up front of everything, and I'm going to plug in my upper bound. So 24 times 12, type it into a calculator. I got 288 minus 12 cubed divided by 9 divided by 3, or 12 cubed divided by 27. I got an exact answer here of 64. Hopefully you guys did also. Minus 12 squared we know is 144, and the 2's canceled already, so 144 divided by 3 gives me 48. And then my lower bound, if I plug in 0, I get 0 minus 0 minus 0, so that's a great big 0. And so final answer on this one turns out to be 176 pi. And that's the end of today's installment, you guys. Keep watching Schoology for my solutions, step-by-steps to problems, so that way you can keep up. And then that way when we have a session together to answer questions, you'll be ready to go. Today's check-in question, if you could please email me back, is to give me your favorite color. Something fast, something simple. Shoot me an email and I can use that for attendance. Talk to you guys tomorrow. Bye.